All right, class, here is 4.2 more on graphs of polynomial functions. So it's about that, what happens in the middle behavior. So far we've learned in 4.1 the end behavior of a graph. So here it is. Let's take this graph right here. The end behavior is that of, we're looking simply at the leading term. This is the important part. This is the leading term. That gives us the end behavior. So what end behavior do we have? The end behavior, again, is that of leading term. Power function. So if I just simply looked at f of x is negative 4x cubed, what would that look like? So negative 4x cubed looks just like the cubic function. Yes, this is the cubic function. However, because we multiply by a negative, what do we have to do with the cubic function? We have to flip it around. Okay. So the end behavior is that of this graph. So in other words, erase just the part in the middle. Okay, so the graph is going to start or come from here and then end down there. Keep going down to negative infinity. Now, what happens in the middle is that we will have the number of possible turning points is one less at most, as we saw very well from 4.1's video, not too many turning points. That's why it's at most one less than, so subtract 1 from the degree of the polynomial. The degree of the polynomial is the highest exponent. Okay, so in this case, the degree is 3. That means we have at most 2 turning points. So between these two ends, we might turn 1 time, 2 times. Oops, my hand kind of slipped there. 1 time, 2 times the most. 1, 2. Yes. Now, the number of possible x-axis intercepts, again, is at most 1, and at most the equal to the degree of the polynomial. So the degree is 3, so we have at most 2 turning points, and at most 3 x-axis intercepts. Now, if you look at this graph that I happen to draw, we only have 1 x-axis intercept, right? That's why it says at most 3. I could have also graphed this polynomial function to look like this. It starts up here, it comes all the way down, turns 1 time, go higher up, turns a 2nd time, and goes and ends down here. So how many turning points do we have? 2, yes. How many x-axis intercepts though? 3, yes. So it depends how, like it could come only this low and turn, right? So then it would only cross 1 time. So that's really how the graphs go, right? At most, no more. It can come turn, it can come turn and then come back again. It can turn and come back again. So this is not going to happen, okay? Just going to end down there, okay? So what we're interested in again is how do we find these x-axis intercepts and how do we find these turning points? I'm going to tell you right now, we cannot find the turning points in the graph on paper. We could very well put it in the graphing calculator and look at the graph and find those turning points. I can easily do that with the graphing calculator, but we cannot use the algebra we have to find them. So it actually takes calculus to find those turning points on paper, again, using equations, things like that. So we can't do that this semester, but we can use our algebra, and that's what this chapter is about. Use the tools of algebra to be able to find these turning points and these x-axis intercepts. Okay, so that's what the rest of the chapter is going to be about. So here it is, factor theorem. How do I find these x-axis intercepts? Well, the factor theorem tells me that a number, let's say k, is called a zero of a function. In other words, it makes the function equal to 0 if and only if x minus k is a factor of f of x. So basically, the zeros of the function are these x-axis intercepts that we're talking about. So here are my zeros. These are the x's that make the function equal to 0. In other words, make the y equal to 0. Right? So we're on the x-axis. All right, so in other words, I'm going to have a point of coordinates k, 0. Okay? So if I plug in k into the function for x, y is going to equal to 0. Yes, okay. So if the zeros of a function are, let's say, x1, x2, x3, all the way to xn, then the polynomial can be factored as some kind of a value at the front that's going to become important. A is important, as you saw from the quadratic functions. X minus x1, x minus x2, x minus x3, and so on. So again, if you think about the quadratic functions we discussed, we factored those quadratics to find those x-axis intercepts, and then the solutions to those factors were your x-axis intercepts. So look back to 3.3. But also backwards, like we always go backwards and forwards. If the polynomial can be factored like this, then these are your solutions. X equals x1, x equals x2. So the zeros are x1, x2, x3, and so on. So here's a function. And it's factored. It's in this form, yes? So find the x and the y-axis intercepts. In other words, what? If I set y equal to 0, right, that simply means that f of x equals to 0. So what I get to solve is this equation. And it's already factored for us, so it should look familiar from solving those quadratic equations by factoring, except for this time I have 3 parentheses. So we're using the zero product rule. And what does the zero product rule say? That if you have a product, and that's what you have, these are factors, so you have a product that equals to 0, then one of the factors must be 0. So either x minus 1 is 0, well, duh, that means x is 1. So here it is, your first 0. Then what? X plus 5 could equal to 0. Well, that makes x equal to negative 5. So again, it's what's subtracted, yes, from x. This is your 0, is what's subtracted from x, so minus 5. And then, of course, x minus 3 is 0, so what's subtracted from x is a 3. So there you have it, okay? And there it is. Okay, so these are your solutions. So the x-axis intercepts, or in other words, your zeros, are 1, 0, negative 5, 0. You don't have to write them as ordered pairs, but I'm showing you that these are the 3 x values that make the function equal to 0. So in other words, that produce a y of 0. Now, to find the y-intercept, I'm making x equal to 0. That's easier because if x is 0, then I have to plug in 0 for the function. Yes, so let me put a different color just to... So these are the x-intercepts. Now, making x equal to 0, that's easy. As soon as I plug in an x value, I just simply put everything in the calculator and then find the answer. So what is 3 times -1? Well, that's a -3 times a +5 times another -3. So I'm going to get a +45. So in other words, if x is 0, the y value that gets paired up with it is 45. So that's the y-axis intercept. Okay. And so this graph, once it's factored, is we very close to finding the graph of this function, actually, because we would know, I know it's not what we want right now, but I'm just going to show you how easy we're going to use this in a minute. So I know I'm crossing at 1. I know I'm crossing at 3. I know I'm crossing at what? -5. I know I'm crossing through the y-axis at 45. And then I have to bring in what's the highest exponent, right? How do I fit in my wave through this? If I multiply these out, that's actually going to be a 3x to the third. So it's a cubic. It's going to go up, come back down, go back up. Okay. I know it's a cubic because if I distribute all this out, I'm going to get at most an x to the third. I have 3 parentheses for x. So x times x times x times 3 is going to be a 3x cubed at the front. The rest doesn't matter, as we saw so many times. Okay. All right. Now, before we put it all together, some factors can be repeating. As we saw in the previous chapter, we solved quadratic equations, and some of our factors were actually repeating. You can have the same 0 or the same solution more than once. We call this the multiplicity of a 0. So a factor can be repeating. In other words, a number can be a 0 multiple times. So as you see, these parentheses, once it's factored out, what does this thing here mean? It means a 2, an x minus 1. Then I have an x plus 4 to the power of 3. So that means this parentheses comes up 3 times. Okay. Then an x minus 3 to the power of 2. So it means that parentheses comes up 2 times. So really, these are all the factors, right? So that's what the multiplicity of a 0 is. So I will say that x equals to 1 is a 0 of multiplicity 1, and that's too much to write already. X equals to -4, so the solution here, -4, -4, -4, when I solve these, is a 0 of, I'm going to just call it M for multiplicity 1. And the multiplicity 3, and x equals to 3 is a solution, in other words, a 0. How many times is that parentheses coming up? 2 times. Yes? So that's what it means to have a higher multiplicity. Now, the multiplicities of these zeros tell you how the graph is going to cross. So a 0 is where you're crossing the x-axis. So if the multiplicity is 1, then the graph crosses the x-axis like a line. so linearly. So at that point, the graph is going to cross linearly. If the multiplicity is even, what does it mean multiplicity is even? So in other words, m is 2 or 4 or 6, not that we'd even go there, then the graph bounces off the x-axis like a parabola, like a quadratic function, like a fourth degree power function. So let me show you what that means. So the graph, in fact, is not going to cross at that 0, but it's going to come and just bounce off. Whatever else might happen afterwards, but it doesn't cross. It bounces off like a parabola. And then if the multiplicity is odd, so in other words, m is 3 or 5 or 7, not 1, because if it's 1, it comes up linearly, then the graph crosses, so it does not bounce, but it crosses through like a cubic function. So by a cubic function, I mean like y equals x cubed. So let me show you what that does. So the graph is going to come, doesn't cross linearly, evens out, and then it moves on. So let me show you what that would look like. So I'm going to, again, we have graphing calculators, you guys. So definitely let's use our graphing calculators to get an idea of what it is. We are lucky that we can. So I don't want to keep forgetting of what the graph goes. So I write myself this thing. So let's go and graph this. So I want to graph 2 times x minus 1 times x plus 4 to the power of 3 times x minus 3 to the power of 2, so squared. All right. Ooh, perfect. There it is. So what do we see? I can't quite point to it, but here it is. At x equals to 1, the multiplicity was 1. So see how the graph at x equals to 1 just crosses like a line, slashes through like a line. At x equals to negative 4, the multiplicity is 3, so the graph comes down, evens out. It does cross, but it doesn't cross linearly like a line. It does cross like the x cubed, comes, evens out, and then it keeps on going. Then at x equals to 3, the multiplicity is 2, so the graph looks just like a parabola there. So it comes, bounces off, and it keeps on going. So here it is. I'm going to zoom out. Well, I had zoomed out, and then I don't know where I'm going. There it is. Oh, yes. Go. Here it is. So this is the graph. Now, altogether, this is a power of 6 graph. And I know it's a power of 6 because I have an x minus 1 one time, an x to the third, so 1 plus 3 plus 2 for the power is a power of 6. So the end behavior is that of a quadratic function. We have how many turning points? Just 3 as you count. So it's at most 4, right? And then, yes, the crossing points should be at most 6. We are actually only crossing 1, 2, 3 times, right? So that's at most 6. But you see the end behavior, and you see how we're crossing through the x-axis, whether it's linearly, right? Like here, like a cubic, or like a parabola for the x squared. So that's pretty cool. And again, you don't have to forget these things because you always have a graphing calculator to help you with this. So if we use the graphing calculator at all in this class, this is the chapter we're going to use it the most. Okay, so let's sketch a rough graph of the functions. First things first, I would like to know what the highest exponent is going to be because I need the end behavior. Do not waste your time figuring out all the terms. We're only interested in the leading term, the one at the front. So at the front, I'm going to have a 3 times an x times the x to the power of 3 times the x to the power of 2, plus a whole bunch more terms that I don't care about because my leading term is a 3. X to the 1 plus 3 plus 2 is 6. 1 plus 3 plus 2 is 6. So in other words, just like the one that we just graphed, the end behavior is that of a quadratic function. In the meantime, I'm crossing where? Where are my zeros? And what are their multiplicities? This should be pretty straightforward. I have a factor of x minus 1 to the power of 1. So the 0 is x equals to 1 of multiplicity 1. My other factor is x plus 2 to the power of 3. If I set this equal to 0, then I'm going to get x is negative 2 of multiplicity 3. Right, that's the power. And then I have an x minus 5 to the power of 2. So therefore, x equals to 5 is a 0 of multiplicity 2. Now, so how is my graph going to go? I'm going to cross at 1. I'm going to cross at negative 2. And I'm going to cross at 5. Okay. So my graph comes from up here. What happens at negative 2? At negative 2, the graph has to cross like a cubic. I could also find the y-axis intercept, so I know where I'm crossing here. It might not be as easy, and we might not be on the graph. To find the y-axis intercept, I have to make x equal to 0, yes? So I have a 3 times 0 minus 1 times 0 plus 2 to the power of 3 times 0 minus 5 squared. So I'm going to show you that's a really big number. So I have 3 times negative 1, that's negative 3, times, don't forget, it's not 2, but a 2 cubed, and 2 cubed is 8, or put 2 to the power of 3 in your calculator, times negative 5 squared is 25, but again, you can put in your calculator, that's negative 600, right? That's not going to happen, okay? So you can just go by hundreds if you want. 1, 2, 3, 4, 5, 6. So that you can just say that's negative 600. Remember, the scaling on the x-axis can very well be different than the scaling for the y-axis. The point is this graph is going to go all the way down to negative 600 before it comes back up. Maybe even lower than negative 600 before it turns and comes back up. Point is it crosses the y-axis at negative 600. Doesn't have to be turning there. And then it comes back up and it's going to cross at 1 linearly, right? A multiplicity of 1. Then the graph comes back up and then it turns because it has to come for 5. And at 5 it bounces off because it has a multiplicity of 2. Okay, so there you go. Now we don't again know these these turning points. You can find them with a graphing calculator. They're not that important. You can. And again, do not graph this to where you break the graph on the paper. So in other words, don't do this because that's what you see in your graphing calculator. So don't show me this on paper, because that's a break in the graph, and the graph does not do that. So it doesn't matter to me or to this point in the story as much of where we're turning. What that matters in this point of the story is where do we cross through the x-axis? What are the zeros? Okay. So let's try this again. Do not worry much about the turning points. So let's see one more time. What would be the leading term at the front? Because I need the highest power. So I have a -5 coefficient. Then I have an x to the power of 1 times an x to the power of 5 times an x to the power of 4. And a whole bunch more, but this is a -5 x to the power of 1 plus 5 plus 4, 10. And so again, do not waste your time multiplying all this out. It would take you forever, and we don't care. We just care about the leading term. That gives us the end behavior. So this graph has an even power, so it looks like a parabola. However, because it multiplies to a negative, this parabola is going to end up being upside down. So it's going to end like an upside down parabola. In the meantime, where are my zeros? Where do I cross? I'm going to cross at x equals 2, 4, and the multiplicity is 1. I'm going to cross at x equals to 1, and the multiplicity is 5. And I'm going to cross at x equals to -2, and the multiplicity is 4. So, crossing at -2, it actually doesn't cross because it has to look like a parabola, so it bounces off. Then it's going to go all the way down, and it's going to come back down for 1. What happens at 1? The multiplicity is even, but different than more than 1, yes? So it's going to cross like a cubic function. And then it's going to go all the way up, and then it's going to nicely, smoothly turn, and it's going to come for 4 where the multiplicity is 1, so it comes through linearly. So it crosses like a line. So if I zoom into this point, it looks like a line. If I zoom into this point, it looks like a parabola. If I zoom into this point, it looks like a cubic function. And again, you can put all of this in your graphing calculator and look at what happens to it along the x-axis. Don't worry about this. These values are going to be super high. It's going to go way, way high before it comes and turns again, but we're not interested in that. Okay, so now let's go backwards and find the equation of a polynomial function, given that a whole bunch of things, and then graph the polynomial. Not a rough sketch, okay? So here are my zeros. So here it is. I'm going to start. F of x is equal to, there can be a number at the front. See how there was a 3 at the front, then there was a -5 at the front. We need to find those values, those a's. I have it maybe even, yes. So there's some kind of a value at the front and then a whole bunch of parentheses. Okay. Now what are my zeros? 5. That means what? I have an x minus 5 for a parentheses. Remember our zero factor rule? And it's got a multiplicity of 3, so it comes up 3 times. I have x equals to 2. That means x minus 2 is a factor. That comes up once. If you want to write the 1, to help you out, that's fine. And then x equals to -3, so x plus 3, also of multiplicity 1. Okay. All right, well, here it is. Okay, then the y-intercept is going to be 0, 15. This extra point here always helps to find a. So that simply means what? That if I plug in a 0 for x, the answer for y, so for the function, has to be 15. So this is how I find a. And again, it's a negative 125 because that's what negative 5 times negative 5 times negative 5 is. So put this in your calculator. That's an a times 750 equals to 15. So therefore, when you divide both sides by 750, you get 15 divided by 750. We can even reduce this fraction, and I'm going to get 1 over 50. Now, this is important because here's my function in the end. Is 1 over 50, again, x minus 5 to the third, x minus 2, and x plus 3. It's a positive value. That's the important part. So if I multiply these out, I just want to get an idea of what the leading term would be at the front, a positive a, an x to the third times an x to the 1 times an x to the 1. That's going to be an x to the 3 plus 1 x to the 5th for my leading term. All right, so it looks just like a cubic, odd degree, and it's turned this correct way. So in other words, it's not flipped about the x-axis. Okay, so I'm crossing at negative 3, crossing at positive 2, and a crossing at 5. At negative 3, it's going to cross like a line. It's going to go wherever, and it's going to come back down, cross at 2, like a line, 1, 1. And multiplicities are 1, then it's going to come and cross at 5, but like a cubic function. And it's going to end up there. Oops. There you go. Here's one more. Degree is 3. So f of x is going to equal to a times. Each of these are a multiplicity 1 factor. So x is 5. That means x minus 5 is a factor. The solution is 2. So x minus 2 is a factor. The solution is 3. So x minus 3 is a factor, right? So these are my factors. And each come with a multiplicity of 1 because, of course, the degree is 3, so the highest exponent is going to be 3. Again, this value here is going to help find the a. So if I plug in a 0 into this function, the answer has to come up to be negative 24. So that's going to be a times 30 is negative 24. Therefore, a is negative 24 over 30. I can reduce as negative 4/5. Okay. So here's my function. Negative 4/5. I reduce by 6. Again, x minus 5, x minus 2, and x plus 3. So find the function. Here it is. Sketch a rough graph of this function. Okay. So we're crossing at 5, at 2, and at negative 3. This is a cubic function. A is negative. So instead of making the function look like a cubic where it comes and it ends, it has to come the other way because the a value is a negative. So the graph got flipped about the x-axis. Yes. And then I'm just going to come through, and each single time the graph crosses linearly, right? So zooming in on each one of these zeros, it looks like a line, okay? And in between is going to turn 2 times the way I see it, and it's crossing 3 times. Okay, let's do one more. So the zeros are, and you can try this on your own as always. Don't forget about the a you have to find. X equals -2, so minus minus 2 is an x plus 2 squared. X minus 3 to the power of 1, and that's it. And again, the y-intercept is 0, -3. That's going to help me with the a. So that's an a times 4 times -3. 4 because it's 2 squared. Equals -3. If I divide both sides by this is going to be a -12. The 3's actually cross out, so I get a is 1/4. So here's my function. Okay, and what would the rough graph of this function be? Okay. Crossing at -2. Crossing at +3. The y-intercept is 0, -3, if you even want to incorporate that. The point is, a is positive. The highest degree there, where the leading term is a 1/4 x to the second times an x to the 1, so that's an x to the 2 plus 3. 2 plus 1 is 3. So it's a cubic function that looks the normal way. So it starts here, ends here. Coming for -2, but the multiplicity of -2 is 2, so it has to bounce off like a quadratic. It crosses at -3. Fine, here is -3. Then it's going to come for 3, and it's going to cross there linearly. So this is my rough sketch of this graph. There you go. So here's 2 more. Find a formula for the polynomial. Same things that we've been doing, but again, going backwards even more. So here it is. I'm going to start with, I want a polynomial function, a times. What are my zeros? I see a 0 at -3. So x plus 3 is a factor, right? And it's looking like it's crossing like a line, so its power is going to be 1. Then I have a second 0 at 2, so x minus 2 is a factor, but it looks like a parabola, so I'm going to put a square there. And then I see yet one more crossing point at 5, and what I see at 5 is that it crosses linearly, so then that exponent should be a 1. Okay. And finally, I need one more point to help me find the a. And then usually the easiest point to read, if I can, is the y-axis intercept. So I see on the y-axis that I'm crossing at 0, -2. So in other words, if in there I plug in a 0 for x, then the answer that I'm going to get is -2. So finally, that's going to be -60 if I multiply all these numbers. -20 times 3 is -60, so therefore A equals to -2 divided by -60, which is +1/30. So that's where the A comes from. So the function here finally is 1/30 x plus 3 x minus 2 squared. Now, of course, it could be to the power of 4. It's an even power. It bounces off. However, just keep it simple. Keep it at the lowest possible degree. So that's how it is. Okay. And here's our last question. Let's try again. You guys try it on your own. Pause the video. I need some A. X, that's a -3, so means x minus -3, so x plus 3, and it looks like bouncing off, so squared. I see a -1, 0, so x minus -1, and I see it's crossing linearly, so to the power of 1. And my last crossing point is at 4, so x minus 4, but there I see it crosses like a cubic, so to the power of 3. And then, of course, I need an A, so let's see, what does this point seem to be? X is 0, and it looks like 40, 80, 120. It looks like that graph goes down by 40s. 4, 8, 12, 16, right? 20, 24, so it goes by 40, so that must be -120. So in other words, if I plug in 0 for x, I'm going to get -120 for y. Okay, so let me put this in my calculator. A times 9 times 1, -4 to the power of 3 is -64. So these are all the values that I have to divide out of -120. So 120 divided by 9 divided by 64. I'm getting a decimal, and that's totally fine. 0.208333. Of course, you can take your calculator and turn this number into a fractional number, and it's going to give me 5/24. So either one of those is fine, and I do not want to waste more time copying everything, so up here at the front I have a 5/24, and that's the answer, and that's the section.